Welcome back, Astronomy 1010, Summer 2. I just hit the record feature, so I'll actually have the lecture recorded this time. We're going to start off today talking about Galileo Galilei. He was considered the father of experimental science and sort of the last history lesson before we get into the more modern Newtonian mechanics that will take up most of today's class. So let's go to lock speaker view. And we'll take some notes on Galileo Galilei. Oh boy, here we go. Let's get up my slideshow to hide my inability to spell. Share screen, share computer sound, and function F5. What was it, 72? There we go. Okay. So Galileo Galilei, excuse me, I forgot the E, was an Italian scientist, and he's maybe pre-Enlightenment scientist, but definitely you could say that the things that Galileo did were more like modern science than some of the earlier history lessons that we had. Galileo was an experimentalist. He built machines, or artificers, as Newton called them, to investigate nature. And he took careful measurements. One legend goes that when he was a young man at 16, he deduced an important property about the period of pendulums by timing the swing of a chandelier using only his pulse. So that's the kind of thing that Galileo would do. That's a classic Galileo move. And insofar as astronomy goes, one of his many major contributions is that he designed the first telescope for astronomical use. Now, Galileo did not invent the telescope. A lens maker named Hans Lippershey did, but he wrote Galileo a letter and said, hey, I just built this long tube with two lenses, and you can increase the magnification, the angular size of something by looking through it. Can you think of something to do with that? And he said, you bet I can. I'm going to use it for astronomy, and pointed up at the sky. So Galileo is the Italian father of experimental science. That's probably the most important note to take to start. And the second note is that he built the first telescope for astronomical use. And his was a small and humble by modern standards, a 3-inch refractor. At some point, I'm gonna teach you guys how to build a simple refractor of about the same size. Hold on a second, the sun is coming out, it's crazy glare here. I always think I'm going to get away with having those blinds open, but they make a mess of things. Okay. So Galileo made a number of observations, and this is what I want to tell you about. Observations of the heavens with his astronomical telescope that convinced him of the wisdom of the Copernican model. The first thing that people usually do when they point their telescope up at the sky is they look at the moon, because the moon is one of the easiest things to look at through your telescope. Although if any of you have ever tried this, you will know that it's not as easy as you might think it is to point a telescope at the moon. You have to wiggle it around a little bit, and it takes some skill. Galileo observed imperfections on the moon. And these imperfections were a direct challenge to the Platonic ideal that the heavens were made of perfectly uniform spheres that were free of blemish. In the In the geocentric solar system, people believed that the heavenly objects were different. They were made of a different material than the crude materials of Earth. And they believed that these planets were perfect idealized spheres, free of blemish. When Galileo saw all these pits and crags, what we call impact craters on the moon, he realized that it was a gnarly and complicated place that showed many of the same crudities that Earth had. And this was a refutation to what the Greeks believed the heavens were made of. The next thing he did is he turned his telescope and looked at stars in the Milky Way. The Milky Way, if you've never seen it before, you have to be in a very dark sky, and you will see a diffuse band of light that you might actually mistake for a cloud at first. And then once you realize that the skies are clear, you'll realize that you're actually looking at this band of light. If you take a long exposure photograph like the one that you see here, you can actually also differentiate the band of light from the so-called darker dust lanes. What you're really looking at here is the disk of the Milky Way galaxy projected at an angle against the sky. Now, the Greeks knew about the Milky Way. They named it the Milky Way. But I'm not sure what they thought it was. Maybe they thought it was some sort of a device that was painted onto the background celestial sphere. But Galileo is no dummy. He knew that if there were stars in the Milky Way that were too faint to be resolved with the naked eye, that meant that those stars were further away than they were. Well, how should I put this? The telescope resolved the band of light into individual point sources. And that meant not all of the stars were located at the same distance from Earth. Now, if I go back a few slides here to the Greek geocentric model, I'm not sure how much of a point past me made about this, but the stars were actually believed to be fixed to a background sphere which rotated around the Earth. For Galileo to suddenly see that some stars were fainter than others basically would have been like blowing the lid off of his entire cosmos. It would have been like a rupture of the sphere, and he must have realized that the universe was a darker, deeper, and scarier place than he thought it was before. And that's a terrifying thought. Or maybe it was. Maybe it was an exciting thought. I don't know. The next thing he did is he observed the moons of Jupiter, which are now named the Galilean moons. One of my favorite parts of this course is when I get to show you pictures of these things. So he observed moons revolving around Jupiter. I'm in my notes here, sorry. Kind of going back and forth. What we now call the Galilean moons. Why don't you guys try astronomy historian with me? Class, why would observing moons revolve around Jupiter be a contradiction to the Greek geocentric model of our solar system? Does that make sense to you, or is that confusing? I just want to see if you can follow the logic here.
Is it because there are now they now know that there are things that don't revolve around the Earth?
That's just the idea. This is an example of an orbital system which does not need to have Earth at the center. Aristotle's idea about Earth was that the center of Earth was like a fixed anchor point to the universe. So it shouldn't have been possible, or it would have been weird, for things to be able to revolve around something that wasn't Earth. Earth was the center of gravitas for the Greek solar system. So it wouldn't make sense for things to orbit around another planet. Here's a cool picture from Galileo's notebook showing his quite terrible handwriting. He's observing the moons night after night kind of drift back and forth against the disk of Jupiter. This is something that I myself have watched many times from the observatory. Watching the moons of Jupiter change their configuration each night is a nice joy. I actually have a little lab on measuring the mass of Jupiter where we do these measurements ourselves, or at least a simulated version of them. If there's time at the end of class, maybe we'll try that out. It's kind of a cute little lab. based on Galileo's own work. The next thing he did is he pointed the telescope at Saturn, and he wrote, Saturn has ears. He couldn't quite resolve the ears into the rings, but he realized that Saturn was not a perfect sphere, but had these little ear-like projections. So he observed Saturn's ears. The next observation of Galileo cost him his eyesight. He pointed his telescope up at the sun, and he observed that the sun was covered in these blemishes we call sunspots. And, you know, one of the first lessons that you're supposed to learn when you buy a telescope, the first thing it says in big block letters is don't point your telescope at the sun. Very, very, even looking at the sun with an unaided optical device can hurt your eyeballs. So a telescope, have you ever taken a magnifying glass and sort of taken all the sunlight and concentrated it into a little dot and set something on fire? I know I did. Okay, so anyways, to look at the sun through a telescope is sort of like doing that to your eyeball. And for Galileo to see sunspots on the sun must have been a profoundly intense revelation, right? Since the beginning of time, people have worshipped the sun as some sort of energy god, right? Think about the Egyptians and you know, worshiping Ra in his fiery chariot going across the sky. To look at the face of the sun and see these black spots at its surface must have been a pretty startling revelation that even the sun itself was not perfect, but was covered in these blemishes. However, of all of the observations of Galileo, probably the most damning of all of them was him observing Venus go through a full set of phases. And this one is actually the most important, but it's a little bit subtle. You have to understand what's going on here. If you tiptoe back to the geocentric model of the solar system, here's the one constructed by the Arab Ptolemy. There is a line that connects Earth and the moon. And what do we call these little secondary orbits again, class? Do you remember what these things are called? There's a name for this. Ooh, excuse me.
Epicycle?
Thank you, Megan. Oh my gosh. Yes, Megan, epicycles, very good. And do you remember what the epicycles were constructed for, why you needed the epicycles? What problem did they solve? An observational problem. You were so good with the epicycles, I thought you might remember. They didn't just do that for fun. Yes, for retrograde motion. Nicely done. Good job. Most of the planets orbited on a secondary circle, which we call the different. I think it's the different. And you'll notice that Mars, Saturn, and Jupiter have difference. But Mercury and Venus don't have difference. Their epicycles are orbiting on a bar connecting between the Sun and Earth. And that is also for observational reasons. The idea goes like this. When you look at Venus or Mercury in the sky, you tend to see them just above or the horizon to the east or the west. Okay, here's the old astronomy rule for Venus. Venus is the first star you see at night, or it's the last star you see in the morning. In other words, if I can use my chalkboard here, if you want to observe Venus in your daily lives, it was up pretty recently. You go out and after sunset, you look west and you will see this hellishly bright star in the sky. Venus is even brighter than Jupiter. The only thing brighter than Venus is honestly the moon. And if you go out another night just after sunset, say a night later, you'll notice that Venus will get a little higher in the sky, and a night after that, it gets a bit higher in the sky, and then it gets to some maximum height that we call greatest elongation. In this case, we call it greatest eastern elongation, because it's farthest to the east. In other words, you're never going to see Venus more than about 40 degrees above the horizon. Because after that, if you go out a night later, you'll see Venus kind of drop back down in the sky, and it will get lower and lower until it reaches the horizon. And then one evening, poof, Venus is gone. But if you wait a few months and then suddenly go out in the morning just before sunrise, yeah, sunrise in the east. A few months later, you'll see Venus pop up there. And then it will repeat the cycle. And Venus will get higher and higher in your sky until it gets to greatest western elongation. And then it will drop back down again. Why am I telling you all this nonsense? Well, for a couple of reasons. One, so that you know what's going on next time you see Venus in the sky. And the second reason is this. Venus and Mercury had to orbit on a bar connecting Earth and the Sun to ensure that the observations didn't get too far away from the Sun. This basically lets Venus chase the Sun. So this here, that configuration would be greatest eastern elongation. And when Venus was over there, that configuration would be greatest western elongation. That's when we see Venus as far from the Sun as possible. It actually makes a kind of right angle with the Sun if you think about it. Now, let's see what you guys remember about your phases of the moon, which I taught you a week ago. Class, what phase would the moon be in if, let me use a spot for Venus here. Let's change our color to yellow, just like Venus is, or make it orange. Suppose Venus was located here. Can you tell me what phase of the moon that would be if the moon were located there between Earth and the Sun? I just wanted to see if you knew your phases of the moon or what, you know? Yes?
Would that be a, that's a crescent, right? One of the crescents?
Not if it's at the orange dot, Adrian.
Oh, the orange dot, that would be full.
Careful, full is opposite the Sun. You're currently between Earth and Sun, right? So you want to try again?
A new moon?
Yes, Tim, a new moon. It's new when the moon is between Earth and the Sun. Okay, so Adrian or Tim or whoever, what about here?
Still be a new moon.
It'd still be a new moon. I can't trick Tim. I tried to trick Tim, but I can't do it. He knows that as long as the planet is between the Sun and the Earth, it's going to be a new phase. Okay, what about over here? What if it's located here, or what if it's located there? So wait, let's clear all the drawings. What would the phases be when Venus was located here and here? You might want to consult your little maps there, your phase of the moon charts.
Would it be first quarter and third quarter?
No, I can see why you said that because they're kind of like at a 90-degree angle to the Sun. But the problem is, Megan, is for the moon to be a quarter phase, it has to be here. It has to be making a 90-degree angle with Earth at the 90-degree angle. Do you see what I'm saying? Here, you're looking at Venus a little bit away from the Sun. You want to try again?
Sure. Would it be waxing gibbous and waning gibbous then?
Ooh. Once again, no, because gibbuses are more over here. All right, so this is where a full moon would be. So gibbuses would be here and here relative to Earth.
Waxing croissant?
Crescent.
Crescents. I would say
Crescent. I could sure go for a waxing croissant myself. Maybe I'll open an astronomy-themed coffee shop and we'll serve moon pies and waxing croissants. Actually, it kind of works if you think about it. It looks like a crescent moon. Actually, well, so that's probably the French name for crescent, right? That's probably where it comes. I bet they have the same etymology if you look it up on dictionary.com. So you're just adding a little Frenchy style. I like it.
Yeah.
Yes, but yes, Janabelle, those are the crescent moons. And so, in other words, if the Greeks were correct that Earth was the center of the solar system, right? Then what you should see is you should see Venus only have two phases, either new phase or or crescent phase. But Galileo sat there and he watched the moons go through a full set of phases, including quarter, gibbous, and full phases, which is only possible if Venus orbits the sun. This convinced Galileo that the Copernican solar system was the correct model of the solar system. And because of this, he decided to write a book concerning the two chief world systems. Here's a page of dialogue concerning the two chief world systems. Galileo wrote this book not in Latin, which probably would have been the sort of default scientific language of the day, but he wrote it in the common Italian language so that everyday ordinary Italians could read it and learn about the solar system. And he also put it in this fun play format. Here's the front page of his first publication of it. There were three philosophers who were having an argument in his book. There was the first philosopher, his name was Simplicio. And Simplicio was the Aristotelian philosopher who believed that Earth was the center of the solar system. Simplicio is pretty much Italian for dumbass, okay? And then there was this Segredo guy. He was kind of always getting pulled between the two philosophers. And then there was Salviati. You can check out his little astronomical devices there. He was the wise, I think Salviati was the wise Copernican astronomer. And they would argue based on some of the observations that Galileo had made. Like Simplicio would say something like, hey, do you know that that Venus always orbits around the Earth on a line connecting Earth and the sun? And then the guy in the middle would say, oh, I didn't know that. And then Salviati would say, yeah, but have you ever actually observed it, dumbass? Because I did. I built a telescope and I looked at Venus. I saw it go through a full set of phases, and that's a little bit difficult to explain, isn't it? And then he would say, oh yeah, I'm actually with this guy. That's right. And because he made the Platonic Aristotelian philosopher look like a dumbass, this greatly upset some members of the Holy Roman Church. And at first they started taking it as a personal insult to the Pope, because during the intervening years between the time when Greeks had developed their model of the solar system and the period in which Galileo was living in, the Holy Roman Church had risen to become, it went from an obscure religion that almost nobody practiced to the dominant political institution of the majority of countries, including Galileo's own Italy. And there were philosophers in the church, theologians like St. Thomas Aquinas, who had used Aristotelian logic to prove the existence of God. So if you were to come out and say that Aristotle was a dumbass and Aristotle didn't know anything about heaven, then that was kind of equivalent to saying God doesn't, people who believe in God don't know what they're talking about. So the ironic thing is Galileo didn't really have anything to say about God. He had something to say about Aristotle. But by using Aristotle to prove God, you have the unintended consequence of deifying Aristotle. That's part of the issue here, right? And so the first inquisition of Galileo, they called him in front of a small tribunal and said, listen, we've understand that you've been teaching this heretical Copernican solar system, but let's face it, that can't be right, and that's going to have to stop, because as you know, the Earth is the center of the cosmos. And Galileo said, all right, you got me, whatever, I'll stop. And he went back to his hometown in Italy and immediately began teaching the Copernican solar system again, because he truly believed in it. And that's when he was called before the Second Inquisition. This is the really scary one. These people, they might be priests, but they were not nice people. These were people who learned torture from the Romans, and it was not uncommon for them to burn people at the stake or to pour lead down their throats and do all kind of horrible manner of things to their fellow human beings that they supposedly loved so much. And Galileo would have been extremely worried about this Inquisition, because his life would be on the line. So they made him stand and put his hand on the Bible and refute the Copernican solar system. They made him claim that the Earth was stationary and did not move. Some people claim that he muttered under his breath, and yet it does move, but he probably didn't do that because he was probably scared. In the end, they decided not to execute Galileo. They merely placed him under permanent house arrest, where he died old, alone, and broke. Well, maybe not alone. I think he was cared for by his sister, but he died broke and blind in his home in Italy under house arrest, and was not exonerated until the 1980s. So anyways, that's what happens when you study science, folks. You can end up like Galileo. Watch out for that. Please make sure that you put into your notes sunspots and the phases of Venus. Okay, I meant for that to take 10 minutes, and instead it took a half an hour. So I'm right on track with my usual, management of time here. May I erase everyone? Any objections? Okay, cool. With Galileo, that concludes our ancient history of astronomy portion of today's course, or of this semester's course. We are now going to move into something a little bit more modern so that we can learn to understand forces and gravitation, and we obviously need to understand gravity if we're going to understand how the solar system works. So this would follow what's chapter 4 in the textbook. Chapter 4 concerns itself with what you might call Newtonian mechanics. Now listen, let's find a book here. Here's the classic tome on Newtonian mechanics, Goldstein's Classical Mechanics. Normally as a physics student, you would take this course not one time, not two times, but maybe 3 or 4 times, each time going deeper and deeper into the onion hole. You guys are going to get the very most simplified and surface layer of mechanics, but the things that you will learn are the bedrock of this material here. It's the very foundation. We are going to study the major contributions that Sir Isaac Newton made to physics and astronomy. Sir Isaac Newton came to us 100 years after the death of Galileo. He was part of a period of history known as the Enlightenment, where men, and unfortunately mostly men, were doing proper science, as described by Francis Bacon. They were making observations, they were drawing conclusions, creating hypotheses to be tested, all that good stuff. And Newton made not just 1 or 2 small contributions, but like 10 or 12 major contributions that completely transformed the way we thought about nature. And that's why his works are so important. He rivals Einstein with who is the greatest scientist of all time, if you want to be cheesy about it. Now, Isaac Newton, although he did many different experiments that we could talk about, we're going to focus on his concept of the force. I don't want to sound like Yoda here, but he is the first person who introduced a physical definition for the term force. And, oh, I'm sorry. Guys, I notice I'm having a little bit of focus issues here. I don't know if you guys can see that on your end. I need to call up my Logitech capture application because I can turn that off. Otherwise, it's going to drive me nuts, and it's going to drive you guys nuts too. I probably should have launched that right at the beginning of class here. Just a second, everyone, or I'm going to lose what little marbles I have left. Okay. Okay, so the autofocus is now decidedly off. And I'm going to focus the camera about 25 or so. Nope, that doesn't look right. Isaac Newton looks blurry to me. Install later. Oh, come on. I honestly think this is a really crappy camera and a crappy application. I'm very disappointed in it. And I hope that someday someone from Logitech will watch these lectures. Ah, there we go. Okay. All right. So Sir Isaac Newton gave us the concept of forces. A force is a push or a pull at its simplest, but Newton is going to put it on a much firmer mathematical footing. He's also going to give us two different concepts that we're going to study related to forces. The first thing that we're going to study are what are called his three laws of motion. And the three laws of motion, as well as his law of gravity, are laid out in his famous textbook, which I am looking for. It's the Principia Mathematica. It's his magnum opus, the work in which he laid out his concept of what a force is, his laws of motion, and his law of gravity. The law of gravity is separate. Gravitation, I guess we would say. The law of gravitation is separate from the three laws of motion. The three laws of motion describe how something moves when it is subjected to an arbitrary force. An arbitrary force is anything that causes an object to get pushed or pulled. So if you have a cannon and you light a match and fire a cannonball with some particular force, the force of explosive gunpowder, Newton can tell you how far that cannonball will travel before it comes to a rest and drops to the ground. So the laws of motion tell you about how things move when they are subjected to forces. In fact, the laws of motion are going to state that forces are the things that cause motion. That's the concept there. Once he does this and he spells out what a force is and how the force works, he then moves on to develop a specific force related to the law of gravitation. The law of gravitation is what we would call in physics a fundamental force. And fundamental forces are really cool because they are ultimately a mystery of nature. Nature herself is the one who invented gravity, and we are all subjected to her laws, and we are all stuck to planets and forced to orbit stars because of nature's inherent design, however you want to look at it. But fundamental forces are not invented by humans, they are invented by nature, and we try to study them to understand how the universe works. Okay, students, how many fundamental forces are there? Did you learn about this a long time ago in high school or grade school or something? I did. I'm gonna hide the non-video participants. What's up with the fundamental forces? Adrian, can you tell me a fundamental force besides gravity?
I don't remember them.
Do you remember how many there are?
No.
Oh, okay. Well, I'm discovering a lot of people, when they get to college, have not heard of them before, which is surprising to me because I had heard about them in high school, but I was also a big nerd and I took physics and chemistry classes, so maybe that's why. I can't remember, honestly, it was too many brain cells ago. I don't know where I heard about the 4 fundamental forces, but as long as I've been thinking clearly, I've known that such a thing exists, the 4 fundamental forces. In fact, you can't really say the 4 fundamental forces anymore because they've collapsed a few of them into even, some people believe that there is, and now this is going to sound like Yoda, some people believe that there is just one force, that all the 4 fundamental forces are the manifestation of the one force of nature, the grand unified theory of everything, and that this force controls the particle destiny of every piece of matter in the universe. All photons and matter from the Big Bang, once it explodes, are all governed by this one law. The problem is we've boiled it down to 4, and we can see that 3 of them are definitely related to each other, but gravity is still the most pesky of all of them. We don't really understand that well how gravity fits in with the other fundamental forces. But when I was a kid, there were clearly 4, and they were gravity, electromagnetism, the strong nuclear force, nuclear, the strong nuclear force, and then the so-called weak nuclear force. In modern physics, we have managed to combine all 3 of these forces, strong, weak, and electromagnetism. Most people agree that we have some proficiency doing this. And this is what's now called the standard model of physics. The standard model of physics is an understanding of how these 3 forces are related to each other. And most of that work was done by building those big particle accelerators and atom smashers, like the Large Hadron Collider, and smashing protons together at high velocities and seeing what kind of exciting particles came out of them. Gravity is still a pesky force because normally gravity is so much weaker than the other forces that you really tend to not even notice gravity until you build up a tremendous amount of matter. You have to literally get a planet's worth of rock and metal before you even start to notice that you're feeling a sticky force, that you're stuck to this planet anymore. At smaller scales, the scales of these 2 magnets, the magnetic repulsion and attraction is zillions and zillions of times greater than the force of gravity between these 2 objects, right? Okay, I'm yapping a blue streak here. So let me tell you some more practical things. Before we get into the laws of motion, there's some stuff that you guys have to understand. In this chapter, our formulas are going to get a little bit more complicated, okay? And we're going to need to use a new system of units for all of our formulas called the Mks system of units. And this means that before we plug any numbers into formulas, we have to do unit conversions using our friend dimensional analysis. The standard quantities that we study in physics are quantities of length, mass, and time. And from now on, our standard unit of length will be the meter, whose abbreviation is a lowercase m. The standard unit of mass will be the kilogram, which is a kg. And the standard unit of time will be a second, lowercase s. Because these begin with m, k, and s, we refer to it as the Mks system. This is one of a number of different possible unit systems that we could use. In the United States of America, so these are kind of your standard metric systems, right? So these are metric units, which most of the world uses. The United States and Myanmar, or Burma, whatever you want to call it, they are the last 2 countries which still use the old English imperial unit system. I wonder, students, if you know what the imperial units are that you use here in the US. What are our standard units of length in the imperial unit system?
Miles.
It's actually not miles, but that was a good guess. Miles are an imperial unit, Janabelle. But it turns out that feet are more commonly used than miles in the imperial system. Mass is one you've probably never heard about, so I'll tell you. The imperial unit of mass is called a slug. Okay, so we use slugs for mass. Slugs are about 32 kilograms. By the way, one of the nice things about having lecture in person is I like to hand around a 1 kilogram mass, a reference mass, so that you guys can feel what a kilogram is like. Now, I can't do that because you're on the other side of my webcam, but I guess I'd just like to say that I like to think of a kilogram as just the kind of thing I wouldn't want dropped in my head, okay? It's not quite a brick, but it's close to a brick, okay? It's maybe like a half a brick or a quarter of a brick or something. And believe it or not, the imperial units also use seconds. Seconds are really old. They go back to Babylonian times. Everybody likes seconds and minutes and things. Okay, so we're going to stick to metric units, which is sort of much more easy and intuitive to understand. There are other units in the metric system besides the MKS, but this is the one that you're going to use. The meaning of this is that when I say MKS units, it means you've got to check all the numbers I give you in your formulas and make sure that you've put them into meters in particular before you try to solve any problems. Let me give you a couple of useful conversion factors that just come up over and over and over again. 1 kilometer is 1,000 meters. That's pretty useful, all right? 1 kilogram is 1,000 grams. For seconds, I find a really helpful conversion is to have the number of seconds in 1 year. That might even come in handy today. So let me put that up there for you. 1 year is 3.15 times 10 to the 7 seconds. Those are helpful conversion factors. Okay, I'm going to erase. Adrian, are you okay with that? All right, here I go. Before we get into Newton's laws of motion, we also have to talk about 3 quantities. I want to talk about speed. I want to talk about velocity. And I want to talk about acceleration, in particular from the point of view of units, okay? So let's first start with the discussion of speed versus velocity. This is usually one of the first discussions you have in a physics class, and I understand why. It's because that the technical difference of these things has a big impact in your understanding of accelerations and forces. So speed, properly defined, tells you how fast something is moving. And in the MKS system of units, it would be measured in meters per second, right? Speed is a change in distance divided by a change in time, if you want to be technical about it. Or I've used the little delta symbols. Do you guys know what the delta symbols are? You've heard that, Adrian? Andrew, how about you? Andrew, have you heard the delta symbol before? Okay, delta means you subtract 2 values. It means d2 minus d1 over t2 minus t1. And if you get sick of writing that over and over again, you just write delta d over delta t, where t is distance and t is time. Speed is an inherently one-dimensional description of motion. It has 2 directions, forward and backwards. Most of the time, when we talk about speed, we are content to neglect the direction and just kind of discuss the forwards and backwards motions. Like, if I tell you that it takes me 20 minutes to get to CCRI, if I tell you I drive from my home to CCRI at 90 miles an hour, not that I would ever actually do such a thing, that hypothetically speaking, I would be describing a one-dimensional set of motions where you assume that I'm going directly from my house to CCRI, and you're neglecting any twists and turns in I-95 South. You're just assuming it's kind of a straight shot. Of course, in reality, there is no such thing as a one-dimensional description of motion, because roads curve and twist, and you speed up and you slow down. you never maintain a perfectly uniform speed. Your speed is different. But a velocity is slightly different in that velocity includes a direction as well as a description of how fast. So we say that technically speaking, a velocity is a speed plus a direction. And the direction adds extra information, right? So if I tell you I'm going to travel at 25 meters per second, and the direction is 30 degrees east of north, this extra bit of information with the direction specifies it as a velocity and not as a speed. Velocities are inherently two-dimensional or three-dimensional descriptions of motion. And that just makes things more complicated. Adding extra dimensions makes things more complicated. For instance, let's consider a classic example from geocentric astronomy, a perfectly circular orbit with perfectly uniform motion. The International Space Station has close to a perfectly circular orbit. In this case, your speed can be constant because you travel at the same rate around the circle, but your velocity is clearly not constant because sometimes your ship is pointing in this direction, and then sometimes your ship is pointing in this direction, and sometimes your ship is pointing in this direction. In fact, at every moment, your direction is constantly changing, and for that reason, a perfectly circular orbit has a constant speed, but a perpetually changing velocity. And that's important because when your velocity changes, that implies that you are being subjected to an acceleration. All right, here's what I really want to talk about. I want to talk about accelerations. An acceleration is a change in velocity, and I do mean velocity, friends, not speed. A change in velocity divided by a change in time. Anyone object to me erasing this little bit here? I need some more board space. Okay. An acceleration is defined as a change in velocity divided by a change in time. If you want to be less precise, you can argue that everything takes time, so you could just call it a change in velocity. That's a simpler way of putting it, but it's not as technically good. To calculate it, we do a delta V over a delta T. That's a change in velocity divided by a change in time. That is, when something changes its velocity, you subtract the two velocities divided by the interval in time. Accelerations can be caused by speeding up, by slowing down, or by taking a turn, like on an exit ramp. You're changing your direction, so an acceleration is implied. And you can feel that acceleration when you go whipping around an exit ramp a little too quickly. You can feel yourself getting pressed against the edge of the car as you do so. It turns out that accelerations are deeply related to forces, but we'll get to that in a moment. Maybe one of the most simple and original accelerations ever measured in nature was done so by Galileo. It's known as the local acceleration of Earth's gravity, otherwise known in physics as little g, and it's the natural acceleration with which objects fall to Earth. First discovered by Galileo in the 1500s. Galileo's discovery of the acceleration is an interesting story. He actually devised a machine to do this, and it still exists today. This is a picture of Galileo's inclined plane, which he used to roll spheres of different densities down this track so that he could measure the rate at which they fell to Earth. He did so because Aristotle claimed that if you had two objects and that one object was massive and the other one was light, Aristotle claimed that the heavier stone would fall to Earth faster than a lighter stone. And he claimed this without ever bothering to investigate or make an observation. Aristotle just claimed it was true because he felt like it should be true, or it sounded good. Galileo suspected it was not true, and to prove it so, he built this machine, and he rolled wooden spheres of various, some were wooden spheres, some were metal, some were made of lead, some were made of, I don't know, copper, some other stuff. I'm not sure what the exact materials were, but I know they had different densities, and based on their densities, they had different masses. He discovered that all the objects fell to Earth at the same, not rate, but acceleration. And he measured this by putting these little bells on the inclined plane. First of all, in case it's not obvious, the reason why it had to be an inclined plane is if he just dropped them vertically, they would move too quickly for him to make a careful count of their velocities. By rolling them down an inclined plane, he can slow the rate of the acceleration. And
wouldn't you have to do it in a vacuum too?
It is true, Tim, that there is a bit of friction due to the atmosphere, due to the air. But the idea being, Tim, that if your spheres are small enough, that resistance from air is going to be quite slight. And you would only notice it if you were measuring it at a high degree of precision, let's say to 4 or 5 significant figures. Galileo wasn't, I mean, he would have loved to measure it to more significant figures. He would have wanted as much precision as possible. But because he didn't have any modern tools like a laser gate or a stopwatch, he literally used these bells so that he could use his ear as the timing device, right? He was just trying to prove, do these things speed up? Do they all go at the same rate? And does the mass of the object matter? And I'm not sure exactly how technical he got, but he got a value of close to 10 meters per second. We can prove that in just a moment, but I don't know, I'm not even sure if he put a number on it, Tim, or if he just deduced that they are speeding up as they're falling to Earth. And you could tell that they were speeding up because of the increase in the tinkling. Whether or not he measured it to any degree of precision is less important because he was the first person to point it out to everyone and say, hey dudes, check this out. These aren't just falling at rates, they're speeding up. And the speeding up does not matter on whether it's made of wood or brass or lead. It's always going to be the same. So yes, if you do this today with even a simple physics setup at a college with our laser gates, we would get some error due to air friction. But he was just trying to work at a much more basic level than that, if that makes any sense. Also, one thing to think about, Tim, is from what I remember of studying the force of friction is proportional to the velocity of an object, right? So when you're going fast, frictional forces become intense. But if you're traveling at the relatively modest speeds that a particle would be falling down this plane, that will reduce the friction. The other thing is it depends a little bit on your surface area and what your material is made out of. And these being relatively smallish spheres would probably actually have a low amount of friction. In fact, as far as I can think about it, I think a sphere might actually be the ideal shape to reduce friction just because you have the minimum amount of surface area for the maximum amount of volume, which is why like some of those trucks, like those big rigs, will have the cabs that are sort of curved to try to reduce the amount of wind friction that will hurt their gas mileage, right? So, so in this case, I suspect that if he had been able to measure it to even 1 or 2 sig figs, he would have discovered that the frictional effects were quite low. You'd have to go out to a higher degree, but it's a cool question, so I want to talk about it. Now, let's say we do the experiment ourselves, students. Let's imagine that we stand at the top of CCRI and we kind of just hold a little ping pong ball up there. And what we're going to do is we're going to do it with a more modern apparatus. We're going to use laser gates to measure the velocity. And we're going to just hold the ball and we're going to let our fingers go and release it. Now, you can tell that there's an acceleration at work because when you're holding the ball, its speed is clearly 0, right? It's not moving. But when you release your fingers, the magic of gravity sort of puts it into motion. So just the act of going from 0 to some speed means that you're accelerating. If we measure it after 1 second, we find its velocity is 10 meters per second. If we measure it after 2 seconds, we find its velocity is 20 meters per second. Let's do a little math exercise together because it's going to turn out to be useful to do so. The local acceleration due to gravity, let's take our V2 and V1 as 20 meters per second. And here, class, I'm going to use blue for my units so that you guys can focus for a moment on the units. 20 meters per second minus 10 meters per second divided by 2 seconds minus 1 second. This is obviously going to give us 10 meters per second divided by 1 second. Megan, what do you think that reduces to?
10 meters.
Ah, you were assuming that the seconds cancel each other out, correct?
I'm wrong.
Yeah, unfortunately, this is a subtle thing that we need to have a talk about. In fact, I suspected that you might say that, okay? So it's actually not 10 meters, but it's 10 meters per second, or 10 meters per second squared. This is the value of little g, our acceleration. Megan, we should have a talk about that. And this talk isn't just about you, it's about everyone in the class, okay? This is really important. One of the professors that I walk past their office every day on the way into work, they have this funny little, professors put those little stupid jokes up on their door, myself included. And one of them is really funny. It says 3 out of 2 people have trouble with fractions, which I think is very, very awesome. Let's talk about how we deal with units and fractions, Megan. This comes up all the damn time. Let's say that I had a little problem like this, which is A divided by B divided by C divided by D. In this case, we're pretending it's an algebra problem, but in reality, where this is going to come up in our class most is with units. What our goal is we want to reduce this into a single fraction with just some stuff in the numerator and some stuff in the denominator. We don't want fractions within fractions because those confuse us, okay? I have little nicknames for all of these letters that come in handy. I refer to A as the top of the top fraction. I refer to B as the bottom of the top fraction. C I call the top of the bottom fraction, and D I call the bottom of the bottom fraction. These are just fast ways to describe all these. We want to try to figure out where each of these letters is going to end up on a reduced fraction. Now, the top of the top fraction is usually the most obvious one. That's just going to kind of end up on the top. The bottom of the top fraction tends to end up on the bottom. And you can see this if you try to do 1/2 divided by 1. 1/2 divided by 1 is just 1/2, right? So if you're on the bottom of the top, you're on the bottom. The top of the bottom fraction also should stay on the bottom. You can see that if you do 1 divided by 1 over 2 divided by 1, that will reduce itself to 1/2, okay? The fourth one and the hardest one is the bottom of the bottom. This is the one that messes you up. And this is the one that goes back up to the top, all right? Now, they proved this to you in some math class, and I could talk to you about it, but I'm gonna tell you to trust me, okay? Megan, let's see if you understand how this relates to what we just did down there. Megan, the meter refers to which letter in this game?
A.
Good. How about the first second, this one here?
B.
Right. This is the bottom of the top fraction. How about the second here?
C.
Yeah. This is the top of the bottom fraction. They both end up in the bottom, and that's how you get 10 meters per second squared. Or you can think of it as 10 meters per second. And that's not just for you, Megan. I'm talking to everyone in the class, okay? We all need to be reminded of these things from time to time because you're not using them every day. Little g is known as the local acceleration of Earth's gravity, first measured by Galileo. Kind of a big deal. More to Tim's point, there was a famous moment. This is just historical funsies. I don't know if I showed this to you last semester, Tim, but this is where Neil Armstrong, or I think it was Neil Armstrong, did that famous hammer drop.
Can we copy to both solar wind?
So Neil Armstrong's over here on the moon, and he's going to attempt to perform Galileo's experiment in the absence of air friction. And one of the reasons probably why Aristotle got confused is if you were to drop a hammer and a feather at the same time, the hammer would seem to fall to Earth faster because you're being bamboozled by the fact that the feather gets a lot of resistance from air friction, right? In the moon's gravity, this should not happen, and he wanted to do a kind of fun demonstration for science students everywhere. The resolution is quite grainy because it's from the 60s. Let's see.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
Beautiful picture, Dave.
I don't know about beautiful, but...
Well, in my left hand, I have a feather. In my right hand, a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time.
Woo!
How about that?
That's kind of cute. Like, you know, they're doing some cutting edge science up there. They've got a lot of research to do that's on the forefront of planetary science and physics. And it's kind of dope that he just took a moment to just redo this sort of, you know, they already knew what the answer was going to be. They weren't confused about that. That was for the kids, you know, that was for the kids and maybe a few adults too. And it's to say, hey, like, let's think about some classic physics that got us here. I think that was a classy touch, if you ask me. Okay. Anyways, now that you've learned about accelerations and you've actually computed an acceleration, we are now prepared to learn Newton's 3 laws of motion. That's where all of this led to. And by the way, Newton himself, he came up with these laws of motion because he was building off of the works of Galileo. His ideas about forces came directly from the experimentation that Galileo had done, which is why Neil Armstrong's saying, he really should have said we got here because of Newton, but he took it one step further back and gave Galileo the credit, which I think is kind of cool. All right, so let's talk Newton's 3 laws of motion. They're kind of a classic. In some sense, he's laying out for us how things move, how things change their velocity. The first law is called the Law of Inertia. And it states an object in motion tends to stay in motion unless acted upon by an outside force. So in other words, objects in motion tend to stay in motion, or objects at rest tend to stay in rest. Forces are the things that change motion. One should recognize that this was a direct refutation to concepts that Aristotle had laid out in his physics book. So he was also pulling a Galileo move of dissing Aristotle by saying this, right? Aristotle had claimed in his treatise on physics, which you can still read today, that a stone pushed along the ground will eventually come to rest by dint of its own gravitas. Aristotle had sort of confused the sideways motion and the downways motion, and he believed that stones, when rolled along the ground, naturally come to rest because they all want to be stuck to the center of Earth, and the pull towards the center of Earth is what stops the motion. Newton realized that there were additional forces that were due to friction caused by the eraser or the stone rubbing along the ground. That if this eraser could be placed in space, free of external media, a single flick would be sufficient to get that eraser flying through space without stopping. In other words, sorry here, oops, let's get out of there. In other words, basically, Newton had kind of already understood what we understand from playing video games like Asteroids. If you ever played the classic arcade game Asteroids, you know that your job is to shoot the little asteroids and you can spin your ship around. But if the asteroids get too close, you can hit your thruster and your spaceship will just sort of set itself in motion and go flying around the screen, and it usually gets out of control pretty fast. Newton didn't have asteroids at his local pizza parlor. He had to be the first person to think this thing up. Not so easy if you haven't seen any science fiction movies as a kid, right? Okay, the second law is his definition of a force. So he said that forces are things which change motion, but he hasn't told you what a force is yet. And it goes F equals ma. Maybe one of the most famous equations in physics. Force equals mass times acceleration. And the units we typically use here, well, let's discuss them. Our mass is usually measured in kilograms in the Mks system. Accelerations are usually meters per second squared. This leads to a new unit of force called the Newton. 1 Newton of force is defined as 1 kilogram meter per second squared, or simply we just call it 1 N. So newtons are also an MKS unit of force. In case this isn't obvious, Newton is MKS because it's defined strictly in terms of other MKS units. There are other units of force. In the metric imperial system, the unit of force are the pounds. Pounds are a measurement of force. In centimeters, grams, and seconds, they sometimes use dynes. Dynes are another obscure unit of force. I'm going to go ahead and get that third law right up on the table here before we go any further. The third law of Newton is subtle and it's profound, but I don't have a ton of time to get into it. It goes, for every action, there is an equal but opposite reaction. So I'm going to put that up here where inertia is, if that's okay. For every action, which is an old-time way of saying force, there is an equal but opposite reaction, which basically means a counterforce. This law helps you understand why it's easier to walk on asphalt than it is on ice. Forces that make you want, oops, sorry. If you want to push yourself forward on the ground, you have to do so by pressing in the opposite direction of which you want to go. There's a lot of different examples of how this comes up in everyday nature. For instance, if I suspend a 1 kilogram weight in the gravitational field of Earth, we know that Earth has a natural acceleration that wants to pull it to the ground. I can feel that force on my finger, and quite frankly, it kind of hurts, okay? If it's not in motion, my finger must exert an opposite force, pushing back up, equal to the force that gravity is trying to pull it down. If we wanted to, we can even calculate it. We could say that if I take my finger and I suspend a 1 kilogram mass from my finger, okay, the force pressing down on me will be 1 kilogram, the mass, times 10 meters per second squared, or 10 newtons of force. So 10 newtons of force is sort of what you feel if you hold a half a brick in your hand or something like that, all right? That's 10 newtons of force. We have a few minutes before we take our tea break, and that gives me time to kind of awkwardly and crudely introduce the law of gravity. I kind of just need to get these things up on the board and into your notebooks because there's a bunch of crunchier formulas that you need to learn for today's lab and for today's homework. So Newton also laid out his law of gravitation in the Principia Mathematica, and it is said that he was inspired by watching an apple fall and realizing that the same forces that must pull the apple to the ground are the same forces that hold the moon in its orbit around Earth. And somehow it led him to the conclusion that gravity is being caused more particularly than anything by masses of objects, that gravity gets stronger the greater the masses of the two objects are, but that gravity also depends upon distance. When the objects are close, the gravity is strong, and as you increase the distance, the gravity gets weaker. Let's go ahead and do some notes on this. When Newton constructed his law of gravitation, he wrote about it in the following manner. So first of all, I need you to imagine that there are two massive objects. There's something like a planet that has one mass, m1, and it's some distance away from another object, which might be one of its moons, m2. This could be Jupiter and its moon, Io. It could be the Earth and our own moon. Newton wrote that the force of gravity is proportional to the product of the two masses, m1 times m2, and inversely proportional to the square of their distance. Where I have used a new operator, you may not have seen this operator before. This Jesus fish looking thing is called the proportional to operator. It's a proportionality symbol. And it is a powerful mathematical tool that scientists and mathematicians use all the time to evaluate things. Proportional to means it varies as, and it's not the same as an equal sign. You can't actually calculate a force, but you can tell by what factor the force will vary. For instance, the Earth, the Moon, and the distance between them lead to some force of gravity which at this point is unknown to us. I'm going to have you calculate it in a couple of minutes. But even though we don't know what the force of gravity is between the Moon and the Earth, I can still tell you what will happen if you double the mass of Earth, or if you double the mass of the Moon, or even if you double both. If you double the mass of Earth and the Moon, you could say that the force of gravity is proportional to the product of the masses. Notice that I'm neglecting the distance right now because that's not varying. And by doubling both masses, I can get a force of gravity which is 4 times greater. That's how one uses a proportionality argument. Similarly, if I double the distance, I can say instead that the force of gravity is proportional to 1 over the distance squared, proportional to 1 over 2 squared, or 1/4 as great. Which in a way is the same thing as saying 4 times weaker. Put in parentheses, 4 times weaker. Newton could only describe it in terms of a proportionality argument, which is still very significant because he knew that gravity depended upon masses and he knew it depended upon distance. But the reason why it's not so easy to turn this into an equal sign has something to do with the units that we use. Class, what are our MKS units of mass again? What are MKS units of mass? Tim, do you know?
Kilograms.
Kilograms, okay. Everyone's hiding on me. So these are kilograms. How about distance, Tim?
Meters.
Meters. And what about newtons? Oh, geez. Wow. Okay. I need some tea. All right. So no surprise there. Forces are measured in newtons. And we need to have an extra term there because kilograms were things invented by humans, so are meters and so are newtons. And the idea is humans didn't invent gravity, nature does. So at some point you have to try to measure gravity. You have to measure how strong would it be if I had two 1 kilogram masses and I separated them by 1 meter. In theory, there should be a force of gravity between them. How strong should that be? Newton did not know how to measure that because he could see that the gravity between two small objects that he could put in his room would be quite weak. The first person who did measure this was a scientist who came a bit after Newton. His name was Henry Cavendish. And he performed an experiment called the Cavendish Experiment, which is pretty clever. Basically, here's a simple picture of it. Oh, I like this. This is a nice diagram. In the Cavendish experiment, Cavendish got these two mass. Ooh, that didn't sound good. Are we okay? Yeah. Oh. All right. In the Cavendish experiment, we have two masses. He used a giant lead sphere and a smaller lead sphere. He suspended the small spheres on a torsional pendulum. That's a thin wire, a thin rod suspended by a thin wire with a mirror attached to it. And he got the two spheres to introduce a small deflection caused by gravity, a very sensitive and tiny deflection that he could measure by bouncing. Well, he didn't use a laser, he used a light source, but you bounce a laser off the mirror and that tiny deflection is measurable because it increases the angle. Whatever. Probably that doesn't make any sense to you guys, but gravity is sensitive enough where with large bowling balls, you can actually measure a small deflection. And when he did this, he deduced something called big G, the universal gravitational constant. We can now rewrite the law of gravitation in its proper form. The force of gravity is big G times m1 times m2 divided by the distance squared, where big G is the universal gravitational constant. It is what we call in physics a constant of nature because it does not change and it has the same value in any situation all throughout the universe. Big G has a value of 7 times 10 to the minus 11. It's a small ass number because gravity is a weak ass force. And its units are meters cubed per kilogram per second squared. You can think of this value as an index of the strength of gravity. Cool. Class, I think we should try a sample calculation, but the first time around you do a sample calculation in this, it takes a little while. So why don't we do our tea break, lunch break now, and when we come back, you all ready for a little break? Pause in the action? Yeah, me too. Okay, so we'll come back just a few minutes after 2 o'clock, maybe 5 after 2, and we'll try our sample calculation then. Okay, love it. I'm gonna pause the recording. Howdy, everyone. I'm back if you are. Okay, let's Windex this board, make it nice and clean. We have to try a sample problem involving the law of gravitation. Has everyone got their Casio calculators? Yeah, woo, like to see that. Andrew, you got your calculator? All right. Earlier I mentioned the force of gravity between the Earth and the Moon. Seems like as good a place to start as any, from what I can tell. Sorry, you guys don't see it through the screen, but this gets really geeky, and it gets harder and harder to take a good note with it. All right, let's go to speaker view here. And our mission is to, excuse me, find the force of gravity between the Earth and the Moon. You're going to need some givens to do this. The givens are the mass of Earth. Excuse me, everyone. 6 times 10 to the 24 kilograms. By the way, that's the little astrological symbol for the Earth. It's a circle with a cross in it. That means mass of Earth. The mass of the Moon is 7 times 10 to the 22 kilograms. And the distance between them, 384,000 kilometers. Our law of gravity looks like this. F equals G times M1 times M2 divided by the distance squared. We also know that our big G is 7 times 10 to the minus 11 meters cubed per kilogram per second squared. Olivia, am I ready to plug all these numbers into my equation?
Yes.
Nope. There's one thing we need to do first. Something's amiss. I want to see if you can find it. Wait a minute, I just lost you.
Let's see.
One of these numbers does not have the proper units. Can you figure out which one it is?
Is it the kilometers for distance?
Yeah. Kilometers are not MKS units. What unit do you need for MKS?
Oh, I forgot. I know I wrote it down somewhere.
Okay. Someone can help her if they want, or
Meters?
Okay.
Okay, Olivia. So your job is to help me convert this from kilometers into meters, and you're going to use dimensional analysis to do it. Okay?
Okay.
I'm picking on you a little bit because I feel like it. All right. So what's your first step in dimensional analysis?
Let's see. So you write, I know it's, would it be the 384,000 kilometers
Yes.
times the division bar?
Yep, that's exactly right. Okay. And now what?
And you would put, let's see, kilometers as units on the top.
And on the bottom?
The meters.
All right. Let's do what dimensional analysis means is it means analysis of units, right? Now, this is the top of the top, that's the top of the top, and that's the bottom of the top. So this is going to end up giving me kilometers times kilometers, which is kilometers squared per meter. That kind of looks like a mess.
Yeah.
That's not exactly what I was hoping to to get out of this.
Okay. Would you do, you have to multiply that by like another unit, kind of? Like to.
No, it's simpler than that. Remember, you're simply trying to go from kilometers to meters.
Yep.
So you need to kill kilometers and
So
have meters.
kilometers would go in the bottom.
That's right. That's
Okay.
right.
Sorry.
That's okay.
Okay.
But one way to remind yourself about why kilometers needs to go on the bottom is to make sure when you
Yes.
write it down on your paper that you cross them out, okay?
Okay. Yeah, that makes sense.
All right. And now your last step.
For the numbers, would
Remember
one
I
go?
gave- Oh, yep.
One go on the bottom?
Yes.
Oh, and then the meters you gave us,
Yep.
which I know I.
Just today.
Oh, 1,000?
Yes. Okay, let's see if we can do this in our heads. How many zeros do you have here
3.
and here?
3.
So what should my final answer be?
384. Oh, meters?
No. 384. How many
Oh.
zeros did you say?
3.
These don't cancel out. This is in the middle.
Okay.
Being in the middle means you're on the top. Those don't cancel out.
Okay. No. Yeah, point times 10. Oh, okay, 10 to the. I want to say 3 because there was 3 zeros.
But there's not 3 zeros. There's 6 zeros.
6. So be to this. Okay, so it's in total between both of them.
Yeah.
Could be.
Like,
Okay.
look, do you agree that 5 times 6 over 1 is 30?
Yes.
That 5 is still on the top, okay?
Yep.
I think my thinking is you might have thought those zeros were canceling each other out at first.
Yeah. At first, yeah.
But this is not on the bottom. This is in the top.
Right.
5 is
Yeah.
5 divided by 1, right?
Yep.
Don't get confused if the position fits.
Right.
Okay.
Okay. Yeah, that
You've
makes
got 3 zeros times 3 zeros is 6 zeros, and your
Yep.
units are meters.
meters.
Now we can plug this into our formula. Get ready, kids. We're going for a little ride. Write down what I write down. The force of gravity between the Earth and the Moon is 7 times 10 to the minus 11. We've got meters, cubed per kilogram per second squared, times the mass of the Earth, 6 times 10 to the 24 kilograms, times the mass of the Moon, 7 times 10 to the 22 kilograms, divided by, watch how I write this, open parentheses, 384 million meters, I'm gonna try to keep my units in blue here, squared. All right, are you guys ready to go, or are you still writing stuff down here? Okay, first time you punch this is a little bit of a trip. We might want to do this together, okay? So follow along with me. 7 exp 11 negative times 6 exp 24 times 7 exp 22 divided by 384 exp6 square key and then equals. Okay, Olivia, what'd you get?
I got lost actually, like in the top portion of it.
I did too.
All right, then we got to do it again.
Yeah.
Do I need to do it slower? Is that the problem? Was I too fast? Okay.
Just a smidge, yeah.
All right, clear it out. Let's try it again.
Okay.
I was trying to do it so that you could see this and me, but you can see it on your papers. Just watch me, okay?
Yep.
So let's go a little slower this time. So 7 EXP is for times 10. 11, or you can do negative key first if you want. 11.
Yep.
Times 6 EXP 24 times 7 EXP 22 times 384 EXP6. Now we need to square this. So we're going to hit square key, which is right up there. And then equals. Oh, wait a minute. I did something wrong. Honestly, I went so slow that I screwed it up. All right, can we try that again? I got the wrong answer there. Wow. I need to go a little, this is difficult for me. Let me try to go slow again. So 7 EXP minus 11, negative key 11 rather, times 6 EXP 24 times 7 EXP 22 divide by 384 EXP 6 square key and then equals. All right, what'd you get?
So I got 1.9.
Yeah.
Like it's 1.99, but you would
So you want
round
to just
that.
make it 2 then?
Yeah.
Sure.
Yeah.
1 sig fig. So 2. There's more to it though, right?
Yes. Times, would it be times 10?
Yeah. To what power?
Would it be 2?
No.
No.
Look, Olivia, the power is right up there.
Oh, 20?
Yeah.
Okay.
You just read it. If you see a number, let me explain this again. If you see a number in this corner, that means you're in scientific notation.
Okay.
All right? Okay, I got a better question for you, a harder question. What are the units?
That's a good question.
Anyone else know what the units are?
Kilogram meters per second squared.
Yes. Kilogram, meter, because kilograms cancel, meters cubed and meters squared become meters per second squared, which is
A Newton.
a Newton, 2 times 10 to the 20 newtons. Olivia, it might have been hard for you to balance out all those units, but one thing you could have done is argue to yourself, well, my answer is a force, right? And I know from my lesson that the units of force are newtons. That's how I was hoping you might do it.
I got it.
All right.
Makes more sense.
Wow, that took a little bit more time than I was hoping. Okay. I wanted to have you guys do another calculation to compare, but Honestly, there's some other stuff we kind of have to do today. I want to talk about tidal forces. And, oh, shoot, no, you know what? All of this gets better if we calculate the force of gravity between the sun and the earth. Let's try one more, okay? This time a little bit faster, all right? And Olivia doesn't have to be on the spot. Someone else can chime in here. Let's find the force of gravity between Earth and the sun. I'm going to do this one a little bit faster this time. The mass of the sun is 2 times 10 to the 30 kilograms. The mass of the Earth is 6 times 10 to the 24 kilograms. And the distance between them is 1 AU, which is 150 billion meters. The force of gravity between the sun and the Earth is 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of the sun, 2 times 10 to the 30 kilograms, times the mass of the Earth, 6 times 10 to the 24 kilograms, divided by 150 billion meters squared. Why don't you guys see if you can punch that in without my help, and whoever gets an answer, just shout it out to me. Tim, maybe let one of these guys try, since you're going to have a bit more chops, right? So anyone besides Tim, I just want to see if you guys can do this now without my help, if I have sufficiently trained you or not. And it can be anyone who shouts it out except for Tim.
I think I got the answer.
Oh, Andrew, I'd love to hear it.
3.73.
Yeah, let's just round it to 4. I'm more interested in the power, though. 4 times 10 to what?
To the 22nd.
Very good. And the units, Andrew?
Would it be the kg times m?
Sure, but more appropriately, when we measure forces, we just use...
Newtons?
Yeah, newtons is the best way to go. Andrew, is this number greater or smaller than the force of gravity between the Earth and the Moon?
It is greater.
Can you tell me by how many times? It's 4 times 10 to the 22 over 2 times 10 to the 20. Do you know how to do this in your head? You don't need a calculator.
Would it be 2 times greater?
4 divided by 2 gives you 2. But here's the issue. You've got 2 more zeros here than you have zeros there. So you've got to subtract these powers.
It would be 10 to the second.
So what is 2 times 10 to the second?
2,000?
No. 2 zeros.
Oh, 2 zeros, 200.
So the force of gravity between the sun and the Earth is 200 times greater than the moon and the Earth. Class, you all live in the ocean state. Most of you know that there are 2 high tides and 2 low tides each day. What's the cause of the high tides?
The moon.
Right. But Andrew, you just calculated that the sun's gravity is 200 times stronger than the moon's gravity. Why does the moon cause tides, but not the sun? Isn't it gravity that's causing tides?
Is it because the moon's closer to us than the sun is?
That's certainly true, Andrew, but here's the issue that I have with that description. If you look at the law of gravity, as we learned about it, Andrew, you can see that we actually included the effects of distance in our calculation. The moon is closer, but when we plugged in the moon's value, it still came out less than the sun's because the sun was so much more massive. So do you see what I mean, Andrew? Like, what is the cause of gravity? What's the cause of tides? Is it distance or is it gravity? No one ever says the moon's distance causes tides. People say the moon's gravity. You know what I mean?
Yeah.
So it's a little bit more subtle and complex than you might think. The moon's gravity is weaker than the sun's gravity. And yet somehow the weaker gravity is causing tides. The stronger gravity is not. And that's because the tidal force is not the same as the gravitational force. There's a profound, significant difference. I'm going to try to give you notes about the tidal force, but I first wanted to confuse you a bit so that you could see that it's more subtle than you might think. Let's take some notes on tidal forces. This is not going to make you a master of tides. It's going to give you a little window into what's going on. Okay. Let's talk about the tidal force. So we're going to start off with a few key notes here. The first note is that, yes, tides are caused by gravity. I don't want you to think I'm saying something different than that. Tides are indeed caused by gravity, but, let's put the but up here. The so-called tidal force is not the same as the gravitational force. They're different, okay? The tidal force, so here's where I'm going to use more precise language. The tidal force is a differential force. The tidal force is a differential force caused by differences in gravity acting over an extended body. In other words, what's usually happening for a tidal force is that you have an extended object, like a planet or a moon, and it's being tugged on by some other object whose size I will neglect. Let's imagine it's a black hole or something. And there is a force of gravity on the front of the object that is different from the force of gravity on the back of the object. And because there's a difference between how strong you tug on the front and how strong you tug on the back, the tidal force ends up being like a, well, like a delta force. And I ain't talking Chuck Norris delta force. I'm talking delta as in the mathematical operator. I'm talking that the tidal force is a change in force. Is Delta Force a Chuck Norris movie? Do I remember that correctly? I don't know. you know, I grew up in the 80s, so these things are important to me, okay? So, all right, the force on the front of an object minus the force in the back of an object. Okay. In fact, one way to think about tides is tides are like a gradient of force. That's technically, for anyone who's had calculus, the tidal force is the derivative of a force. And in calculus, when you take derivatives, you turn a quantity into a gradient. Let me explain what I mean by that. I'm going to show you guys, gradient is also a tool in Photoshop. If you guys play around in Photoshop, let's look at a black to white gradient. A gradient is a mathematical concept, but it has visual and auditory counterparts. Here you can see a black to white counterpart, where you could imagine these numbers which represent the intensity of pixels. This could be 100% brightness, and this could be 0% brightness. And as you fade from front to back, there's a decrease in the pixel intensity. There's also a mathematical equivalent of this. There can be a temperature gradient. If it's warmer next to your heater than it is next to the window in wintertime, there might be a gradient of temperature in your room. There can also be gradients in gravitational forces, and that's what tides are. So here's the Earth and the Moon. Remember that in the case of the Earth, the diameter of Earth is about 12 to 13,000 kilometers. That's roughly 3% of the distance to the moon. So that means there's a 3% difference in distance from the front side of the Earth and the back side of the Earth. The result is that the front side of the Earth gets tugged on more strongly than the back side of the Earth. But from the Earth's reference frame, something kind of funny is going on. The Earth just feels a difference in force between the tug on the front side and the back side. And the Earth will experience that as a side-to-side pulling apart shear force. It's easy enough to see why the front side of Earth will get tidal forces bulging the water towards the moon. The high tide that points away from the moon is a little bit more complicated to understand. You could think of it as the center of Earth getting tugged away from the back oceans, or you could think about it from an Earth-based perspective, where Earth is just getting a tidal shear force pulling it apart. Now, the sun's gravity is stronger on the Earth at all points. However, the gradient of force that the sun exerts, the difference between the front side and the back side, ends up being smaller for the sun than for the Earth, because the diameter of Earth is a much smaller percentage of 1 AU. So it can be true to say simultaneously that the gravity that the sun exerts on the Earth is at all points stronger than the moon, and yet the moon's tidal force, the separation of force, is greater on the Earth than the sun. In fact, as I'm about to point out, the sun's gravity does have a very small effect on tides. And during full moon and new moon, once a month, we get these unusually strong tides called spring tides, where the sun's gravity amplifies the moon. And then during first quarter and third quarter moon, we can get these so-called Neap Tides. Neap Tides are where the gravity of the sun weakens the gravity of the moon. In fact, if we were to find a picture of tidal variations, I don't know, maybe we could do it in Narragansett Bay. Tidal variations in sometimes I have better luck with this than others. There was one day where I found like the most perfect graph that really explained it all. This is over the course of a week. Let's see if we can change it for a month. From June 13th to July 14th. The maximum range is 31 days. Okay, so let's do July 12th. Fine. I don't know. How many days are in June again? Fuck. This isn't working. Ooh, that's calendar view. Plot daily view. Oh, hey, can you guys see this? Do you guys see where the spring tides and the neap tides are in this diagram? Where's the spring tides?
Really early on in the graph, like right there.
Yeah, there's the spring tides. And there's the neap tides. It's the second amplitude that's going over the whole thing, right? You get a high tide and a low tide, but some of the high tides are stronger and some of the low tides. So this must be, so I bet, now it's actually a little bit more complicated, right? Because the tides that you experience, say in Narragansett Bay, will also depend on the local shape of your river and how water flows through it. And sometimes there's a bit of a lag. The moon actually pulls on the Earth, but because of Earth's rotation, the tides can sort of trail the moon. But I'm betting, oh, I'm going to go out on a limb here. I'm not sure if I'm going to do this right, but I'm betting that third quarter moon was somewhere around June 13th. Someone gave me a nice lunar calendar. Oh, wow. Look at this. Third quarter moon was exactly on June 13th. How cool is that? Perfect synchronization. That's lovely. I love it when I sound like I know what I'm talking about. That's always nice. Okay. Wow, that worked out really well. I want to remember that website forever and ever. So I'm going to steal that. Okay, cool. Once Newton came up with his law of gravity, he was able to learn some deeper level things about nature, like, for instance, this tidal force. And one of the weird things you can do with Newton's laws is you can take his law of gravitation and you can take his second law of motion, F equals ma, and you can combine them in ways that re-explore some of the wisdom that people like Galileo and Tycho Brahe and Kepler discovered. So there's a section of our notes that we're going to do now. Normally I like to justify it a little bit more, but I kind of have to get to the point because we only have 20 minutes left, and I need to explore this for our homework or for our lab today. Newton did this funny thing where he basically re-examined Kepler's laws of planetary motion, but now from the perspective of gravity. And he discovered that Kepler's laws were really valid and they were important contributions to science, but he kind of picked apart the machinery and saw a little deeper into the engine there. And let's call this section of your notes Newton's version of Kepler's third law, or Newton's version of Kepler's laws of planetary motion. These are both the kinds of things that I'm going to want to test you about. Maybe we could just stop for a second and talk about the test. When is that scheduled to happen? It's probably coming up kind of soon, huh? These summer classes are ridiculous. Let me just do a quick look at your syllabus. I'm doing this as much for myself as for you guys. Summer 2, 10-10 schedule. Our date today is 7/13. Okay. Class, technically speaking, our exam is supposed to be this Wednesday, but I don't think we're ready for that just yet. I think we're going to push it back to a week from today. Is everyone okay with that? So let's do one more class and one more set of lectures before we do the midterm. I think If I had thought about this correctly, I'll send an announcement about that. We're going to push it till next Monday. That'll just give us a little more time to train on these kinds of laws before we head into it. I'll also have a lot of help to give you before the exam. We're going to do an office hours that day, and you're going to do a lot of sample problems. So you'll get some training, okay? Wow, I'm really glad I took a look at that. So let's talk about Newton's version of Kepler's 3 laws. These are the kinds of things I'm going to want you to know about during the test. Newton's versions of Kepler's 3 laws. And those are his laws of planetary motion, but I'm running out of board space there. Let's use this as a chance to review Kepler's law of motion. What was Kepler's first law of planetary motion? Not Newton's law of motion, but Kepler's first law of planetary motion. There's a difference. This is something that past me would have taught you about on Friday's lecture.
Is it the Law of Ellipses?
Beautiful. And Adrian, while you're there, could you just read that out for us so we can think about it together?
A planet orbits the sun on an ellipse with the sun in the center.
No, not with the sun at the center. This is is that what you have in your notes?
Yeah.
Did I say that in lecture?
Perhaps. Center, I think I wrote center as like what it revolves around, not necessarily right in the center.
No, 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 no. This is an important distinction. Adrian, we need to clean this up right now. Adrian, in an ellipse, this is the center. The sun is not there. Let's look at a diagram of, didn't we make a diagram of an ellipse last time? The center of the ellipse is here, Adrian. But the whole point of Kepler's first law is that the sun is not at the center, but the sun is at a focus point. Does everyone else have that written down? Did I actually say that? I can go get that video up and look at it right now. Who else took notes besides Adrian?
I have that it's located at a focus point.
Okay, Megan's got that. So,
All right.
Adrian, I think I understand.
Sorry, I think I meant focus point. I just didn't write it like that.
Sometimes you kind of write it in your own way to try to help interpret it or understand it in your brain, but you may have inadvertently, Adrian, just stepped on a huge landmine without realizing it. I think because you were learning it, you thought that by translating it to center, it might make it more intelligible to you later on reading your notes. But without thinking about it, Adrian, you actually hit a big landmine there, the center and the focus point. So if you don't mind, Adrian, would you please correct that in your notes? Okay, that's a big deal for me. Okay. Now, in Newton's thinking about it, Newton was able to realize that this law had problems as stated. It's fine if it's a planet orbiting around the sun, but if the laws of gravity apply to any 2 objects with mass, Newton could see that it would be possible to have orbits around objects that had very similar masses to each other. For instance, a binary star system. Or in the case of Pluto and Charon, Pluto and its moon Charon could actually be considered a binary planet system because the moon Charon is very, very close, well, reasonably close to the mass of Pluto. Let's look at a picture of Pluto and Charon in case you've never seen them before, because they look freaking cool. Here's an image of the 2 objects from the New Horizons mission. So you can see here from this family portrait that while Charon is smaller in size and in mass, Charon is roughly 1/3 the mass of Pluto. And because of this, these objects both have a significant effect on each other's gravitational orbits. The moon can orbit around Earth on an ellipse with Earth at a focus point, but that's not the case for Pluto and Charon. What Newton realized would have to happen is if 2 objects had similar masses, instead of one just simply orbiting the other, that the 2 objects would orbit about a common center of mass. The idea behind the center of mass is that it's kind of like a weighted average based on how much more massive one object is than the other. So in this case, in the first case, if star 1 and star 2 are equal to each other, the center of mass is in the middle. If star 1 is 4 times as massive, then the center of mass will be 1/4 the distance between the two objects. If star 1 is 10 times greater, the distance would be 1/10 the distance between the two objects. In the case of the sun and Earth, the sun is quite literally millions of times more massive than Earth. So the center of mass of the Earth-Sun system is 1/millionth the distance from Earth to the sun, and 1/millionth of 1 AU is 150 kilometers, which is less than the radius of Earth. So in actuality, the Earth does not exactly orbit around the sun with the sun at a focus point, but it's instead doing something that looks a little bit more like 68, more like this. The Earth orbits a point somewhere inside the belly of the sun on an ellipse, and the sun also is orbiting a point somewhere inside the belly of the sun. In other words, the sun actually wobbles on its axis due to gravitational interactions from the other planets. This is what the orbit of the sun would look like if there was only one planet in our solar system. And the planet that has the biggest effect on the sun is obviously Jupiter. Saturn and Earth are tied for second place, and all the other planets combined are third place. So the sun's orbit is actually a very complicated wobble due to the gravitational tugs from the other planets. This isn't a small issue, students. This is actually a big issue in modern astronomy, because as you may have heard, we have since discovered planets outside of our solar system. And we've done this by using a powerful telescope called the Kepler Space Telescope. I don't know if I have a picture of it, I guess I don't, to observe the wobble of stars and infer the masses of planets outside of our solar system. So today we discover planets outside of our solar system by measuring stellar wobble. In fact, Tim, you told me about some cool new result in astronomy. Were you the one who told me about the new planet they discovered, or was that the other class I was having this discussion with?
It was the other class, I think.
Okay. Recently, I don't know if you guys heard, but they discovered a new planet around Proxima Centauri, the closest star to Earth. And it turns out to have an Earth mass planet in its, or a planet that would be close to Earth's mass at just the right distance from the parent star. New planet, Proxima Centauri. In case you are interested in it, because it's kind of a cool, I'll put it into the chat log. If I start going on a tangent, I'll ruin this whole class. But the thing I wanted to tell you is that, here I go on my effing tangent, sorry. They use this technique of stellar wobble to discover a potentially habitable world around the closest star to Earth. That's super cool, because it's around 4 light years away. Well, I'm not going to say it'll be easy to get to it, but it's kind of cool to think that one of the closest stars to our own sun, oh crap, you have a paywall here. Well, I should have given you a different, maybe space.com would be a better. Anyways, check this out. It's interesting. Just trying to relate your lecture on classic astronomy into some current events there. Okay, so let's write down Newton's version of Kepler's first law. The idea, and we'll call this NK1, two masses orbit on an ellipse with the center of mass at a focus point. Where the new concept here is the concept of the center of mass of the two systems, sometimes called the center of gravity. By the way, we really should, if we want to be super technical, cross out ellipse and replace it with the word conic section. This was another discovery that Newton made. Newton discovered that while ellipses were possible, that there was a whole class of shapes which could create gravitational orbits known as conic sections. And function F562, there are 4 different ways that you can slice through a cone. And depending on whether you slice it horizontal, at an angle, or completely vertical, you can get circles, ellipses, but you can also get these shapes called parabolas and hyperbolas. Kepler believed that planetary orbits needed to be bound, but Newton discovered that gravity would allow for the fact that if the objects had a velocity which was too great, that gravity would still deflect or change their orbit, but they would undergo a type of gravitational slingshot and get flung off the sun, never to return into deep space. In other words, there are 2 types of orbits. There are bound orbits, which are circles and ellipses, and there are unbound orbits like parabolas and hyperbolas. Kepler had nothing like that in his conception of how orbits worked. So Newton's version of Kepler's first law is much more sophisticated than Kepler's version. Okay, Adrienne, while we're checking your notes here, what was the second law of Kepler?
Law of Arius? I can't.
Arius.
Arius.
Although it would be nice if there was a law of Arius too. That way we knew just what the best opera should be. Okay. Yes, the law of Arius. You know what? Maybe what happened, Adrian, maybe it was difficult. I guess normally if I'm writing notes, you can ask me what's going on, right? If the notes are hard to read. Is it possible that the notes were hard to read on the screen on Friday? Who knows?
I don't remember.
All right.
I don't think so.
Oh, okay.
I just wrote the wrong words.
That's okay. That's all right. The law of Arius. All right, so what did it state? Let's check your notes.
Planet sweeps out equal units of area in equal intervals of time.
Yes, that's perfect. A planet sweeps through equal units of areas in equal intervals of time. And that was this picture here. The planet's going faster when it's closer to the sun, slower when it's farther from the sun. And if you trace out the area, the planet keeps a consistent area as it travels around the sun. Now, this law turned out to not need any modification at all. The law of equal areas was simply true. But Newton discovered that there is a reason for it. The reason is something called the conservation of angular momentum. I have words to say about angular momentum. I will not say them now. I'll save them for next class, okay? So make a note. Tell me about this next time. That's because I wanted to get to the third Newton version of Kepler third law. Okay. By way of what we're about to do, I'm going to introduce something called Newton's version of Kepler's third law. This is kind of a big deal in astronomy. And because of that, it's going to get its own nickname. We're going to call it NK3. But I think a good way to introduce this is to sort of contrast it with Kepler's third law. so that you can notice the differences. Kepler's third law was a math equation that said p squared is equal to a cubed. And in this formula, p had to be measured in units of years, and a had to be measured in AUs. So p is the period of the planet measured in years. A was the distance between the sun and the planet measured in AU. Newton discovered that Kepler's third law would only work for orbits around the sun. And that means it will work for a planet, and it will work for a comet or an asteroid, but it would not work for, say, a moon. It would not work for a satellite or a binary star system. Newton discovered that he could make it work for any two orbits if he added the effects of gravity. And his version looks a little crazier. P squared is equal to 4 times pi squared times a cubed divided by big G times the sum of the two orbiting masses. Here the units are different. P is to be measured in seconds. A is measured in meters. And the masses are to be measured in kilograms. And this equation works for any two masses. It's more complicated, but it's universal. In fact,
they use Kepler's third, like that comet. Was it Neowise?
Is this a recent comment?
Yeah, the one that's up right now.
Oh, I'm a little out of the loop, Tim. Let's take a look at it. How do you spell it?
Neowise.
And what were you saying about Kepler's third law?
So they're saying it takes 1,000. It won't be back for another 1,000 years. How does that work? They just track the period it takes or the distance?
No, because this is the first time. So I see your question. Here's what they do. They make a map of its orbit, and they fit an ellipse to that orbit. They measure the parameters of the orbit, and that lets them calculate the semi-major axis. Okay, so let's see if we can just show you a picture here, because I think a picture will help. So here you go, and here's a little model of the orbit of the comet. You can see that, oh shoot, this is too small here. Wait a sec. Usually what happens is you don't notice the comet until it starts getting pretty damn close to the sun. Oh, and it has a nearly, not quite parabolic orbit, but almost a parabolic orbit. That's interesting. That means it's almost traveling fast enough to be unbound from our solar system. What happens is the comet is on some very, very large ellipse, but you really don't start noticing the comet until it gets kind of close to Earth and the sunlight heats it up and makes it bright. And as soon as you see it, everyone around the world starts tracking it. And they keep tracking it until it gets outside the Earth's orbit and kind of disappears and gets too faint to see. But you model the orbit by keeping track of its position, and you calculate its perihelion when it's at its closest point. And there's an equation that lets you go from the perihelion distance to the semi-major axis. And then you use Kepler's law to get the period. So obviously they didn't measure the period, because I doubt 6,000 years ago anyone was around. Someone was around then,
Yeah.
and they may have even seen the comet, but they might not have understood its significance, right? So no, you do it entirely by modeling the geometry of the near parabolic orbit.
So with that, the lab we did last week,
Yep.
we could have used that to calculate its period.
Yeah, I hate to say this, you guys got shortchanged a little bit. There's a second part of that lab where I give you a sense of how that can be done. And in the second part of the lab, what we did is we have a bunch of photographs of the moon at different parts of its orbit. And we actually measure small changes in its angular size and then use the small angle formula to convert that into a distance. It's a really cool lab, and it gives you a sense of how you might be able to go from observations to an actual computation of the orbit. So in a way, it's like some real ass stuff. But what I've discovered over the years is it tacks on like a whole extra hour to the lab. And especially now with you guys sitting for 5 hours with me in class, although it was a cool exercise, I at some point decided that the hell I was putting you through to go through your 6th hour was maybe not worth the extra learning that you got. It was kind of a hard toss-up. But I decided that most of you would rather just make dinner or something, you know? But so, in fact, if you have the instructions for that lab, you can look at it yourself and see it. But it is possible to do these things just from observations on Earth. And that's the heart of what real astronomy is about. Taking your 101 level stuff and then going out and doing something badass with it. So I'm glad that you brought that up, Tim, because I'm ashamed to say it, but Neowise slipped under my radar. So I'll have to bone up on this. I don't know how long it's been around for, but did you see this within the last few days, or how long ago did you see this?
Last few days. I think it's going to be up until like the 21st is when it's going to go out of view.
I wonder, I'd be curious to know what its maximum magnitude was, if this is observable from us. So this was seen through an 11-inch telescope. And that's, oh wait, you guys can't see what I'm doing here. Hold on, let me share my screen. The first question I always think of when I learn about a new comet, Tim, is, will we be able to see it through the Jacobi Observatory, right? Because it would be kind of cool to take a picture. So this was a picture of it taken with an 11-inch telescope. Ours is bigger than that, but he might have more talent or a darker sky. I wonder where Ray's observatory is. This was just taken by... I'm wondering if his sky is less light polluted than our own. That's a curiosity to me. There's all right, well, I don't know where Ray is, but I guess I'm getting wide to the point here. Okay, this is what happens when you ask me interesting questions, Tim. I go down the rabbit hole. Listen, what we're gonna do is, as you know, every time you introduce a new formula, especially one as difficult as this, we need to do a sample problem. But because this sample problem takes a while, I've decided to turn this into a lab, okay? So we are now going to transition to this evening's lab, or this afternoon's lab portion of the course. And this is also going to knock a little bit off of our homework next time. So introducing... this is this lab 5 that we're on now? Or is this is lab 5, wow. Lab 5 is going to be on calculating the period of the International Space Station, okay? And sometimes I move over to the desk to do this, but I think it'll probably just be less, just as good if we do this on the board, okay? So this is basically like a calculator training exercise and a complicated problem set that you guys will turn in. And you can just take a photograph of what we do here and submit that to me. So first of all, for those of you who don't know about the International Space Station, it's an orbiting satellite above Earth. So I'll just type ISS into Google here. And it's maintained by NASA and the European Space Agency and the Russians. And people live up there year-round on this space station. And they do fun experiments in microgravity. They do all kinds of variety of science experiments, some biological, some on human exposure to spaceflight. You can actually watch the YouTube videos that the scientists on the ISS make, where they explain some of the crazy technical research they're doing, and sometimes just simple things like Chris Hadfield's YouTube videos on how to make a peanut butter and jelly in space, or how to clip your toenails in space. There are all sorts of ridiculous things that are fun to watch. Mostly it's fun to watch people floating around in microgravity. There's one that I'll show you a little later where they have this part of the ISS called the Cupola, which is this observation lounge. Let me just type this into Google real quick, ISS Cupola. And you can actually just look at the Earth below and just I think this is what people do on their day off on the ISS. You sit inside this little hatch and you basically just look down at Earth. It actually looks really cool and super sci-fi like. Yeah, here's a picture of Tracy Caldwell. And you kind of watch the Earth rotating beneath you and you can observe landforms. Very cool. It must be an incredible experience to sit inside this ISS Cupola. Now, I know from observing myself that you can actually see the ISS every day or every other day, maybe every couple of days. If you know when and where to look, you can actually see it go overhead as a bright star-like object. It looks sometimes brighter than even Venus, and it just moves across the sky for about 2 to 3 minutes, and it's kind of a cool thing to do. And because it's not orbiting the sun, it's a nice chance for us to try out Newton's version of Kepler's third law, which is the point. So let me draw the setup here. So our goal in this lab is to find the period of the ISS using Newton's version of Kepler's third law. And to do so, I want us to start by drawing a nice diagram of the setup here. So here we have the Earth, all right? And we have the International Space Station hovering above us. The height of the International Space Station is about 400 kilometers above the surface of Earth. That's much less than Earth's radius, 6,400 kilometers. We're also going to need the masses of the two objects. The mass of the Earth is 6 times 10 to the 24 kilograms. The mass of the International Space Station is 400,000 kilograms, or 400 metric tons. We also have our equation. P squared is equal to 4 times pi squared times a cubed divided by big G times the mass of Earth plus the mass of the ISS. Let's start by identifying our A. Megan, do you think you can identify the A? No? Okay. Nick, you want to take a guess? Andrew, Janabel, anyone think they know what the A would be in this case?
AU.
No. Okay, so you just gave me a unit, Janabel, and that's not the units we're going to use. A needs to have units of meters. But before you talk about the units, Janabel, we got to figure out what A is. Like, what does A represent in this calculation? Yes, try again.
Distance between the sun and planet.
Right, but in this case, we don't have a planet orbiting the sun. In this case, we have a satellite orbiting Earth. So can you modify that in some way that makes sense for this situation? Do you see what I'm talking about?
I'm trying to. I'm
Okay.
I'm trying to gather some information from the notes that we just wrote.
Right. No, you did the right thing. In previous problems, A was always the distance between the planet and the sun. But the whole point of today's lab is to try this out for a different type of orbit, an orbit where a satellite's orbiting Earth, and we see how it is similar.
I'm not sure.
Adrian, do you see what I'm talking about?
Is
Well,
it
maybe-
sorry, is it the distance between the ISS and the planet?
Yeah, so what would the value be?
Would it be 400 kilometers?
Yeah, I can remember when I made that mistake back in my early days of astronomy too. You had the right thing there. You had the right idea. It's the distance, but one of the things I may not have been explicit about, it's the center to center distance. See, the satellite doesn't orbit the surface of Earth, it orbits the center of Earth.
So then it would be 6,400 kilometers, right?
Huh?
6,400 kilometers or not?
It's actually the sum of the radius of Earth plus the height of the satellite. It's the center to center. A is the center to center distance of the two objects. Let's write that down. A is the So A is the radius of Earth plus the height of the shuttle, and therefore it is 6,800 kilometers. Now, Janabel, you seem like the perfect person to talk to about units. You mentioned AU. Unfortunately, that's not going to work. We're going to need meters here. Would you be kind enough to help me convert this from kilometers to meters?
I'll try. Let me go to my notes.
Yeah, let's go look at those 4 steps of dimensional analysis together.
Yeah. Okay. You're gonna write down the number to convert, and that's going to be 6,800 kilometers.
Beautiful. Okay, I like it.
And you're gonna multiply by division bar.
Okay, I like that too.
You're gonna put the units first to make them cancel out. So
Okay.
you're gonna put meters, M, on the end of the division bar.
But top or bottom?
Top.
Okay.
And you're gonna put kilometers in the bottom.
Very good.
You're gonna put it over 1. You're gonna put a 1 as a denominator.
Yep.
You're gonna put the numbers in second using conversion factors.
Oh, by the way, you're not always putting 1 in the denominator. It's been that way for the last couple of conversions, but sometimes 1's on top.
Okay.
So, in fact, I thought you were already giving me the numbers. So now.
Oh, okay. And then on top, and we're converting to kilometers. So you're gonna put times 10.
Times 10. You need to know the number of meters in a kilometer, which you can get a couple of pages back in our notes today.
Okay.
How many meters are in kilometer?
1,000.
Yes. So 1,000 goes on top. 1,000 meters You ended up being correct that the 1 should go there, but I'm
Okay.
afraid
Oh,
that you thought that 1 goes there by default, and that's not
I
true.
did.
All right,
Okay.
yeah. So we had to clear that up, all right? Okay, now you can actually do this in your head, right? Janabelle, you've got 5 zeros, but you're going to treat the 8 like a 0 as well. So you're going to get 6.8
Times 10 to the 5th power.
You've got to go 1, 2, 3, 4, 5, 6 to get past the 8, all right?
Okay.
And that's meters. Okay, now we have our A. That's looking good.
Can you put the camera down a little bit, please?
Yeah.
Oh, there. Thank you.
Next thing we got to do is we got to deal with the mass. Sometimes the sum of the masses here can be considered the total mass of the system, which I will call M total. It's the mass of the Earth plus the mass of the ISS, 6 times 10 to the 24 kilograms, plus 400,000 kilograms. Let's go ahead and add those two up and tell me what you get. So we're going to do 6 EXP24 plus 400,000. Nick, why don't you tell me what you get? So I can hear your voice too.
I got 2.4 and 30. Can you hear me?
Oh, are you quiet? I guess you're quiet, huh?
Yeah.
All right. Either you got to sit closer, or if it's too much of a pain in the ass, I can call in someone else. I just wanted to get you involved. I was thinking of something yellow.
Can you hear me now?
I can indeed, sir.
Okay. 2.4 to 30.
Did you add or did you multiply?
Oh, I may have. Hold on. Let me try it again.
Yeah.
I got it again.
What'd you get?
I got the same thing as before. I'm doing something wrong.
No, what did you get though?
2.4 over 30.
Yeah. Are you using a Casio?
Yeah.
I was thinking, Nick, this is how I do it. Watch me. I just do 6 EXP24 plus 400,000 equals.
I must have hit times again.
Yeah. What'd you get this time?
6, then 24.
Wait, isn't that just the mass of Earth?
Yeah.
Weren't you supposed to add the mass of the ISS?
Does something cancel out?
What did you get, Olivia?
I got 6 to the 24th power.
6 times what? But isn't that just the mass of Earth?
Yes.
Adrian, what's going on here?
It's so far back in the significant figure line that it doesn't, like, the precision doesn't
Allow it to
be shown, yeah.
Yeah, so I was playing a little trick on you guys, and Adrian knew what the trick was, so she was laughing, or he was laughing, sorry. Adrian, you were exactly right. So Adrian, this is a trick that you may have seen before in your mathematical sojourns, because you said that you've taken a few math classes, right? So not everyone has seen this, and this is important that you guys learn this trick, because this trick, you would never think of it on your own. You have to have someone like me trip you up and trick you, and then you can see what's going on here. So just to be very explicit, this number, although it sounds big, is a really, really tiny percentage of that number. So if you try adding them on your calculator doesn't have enough decimal places for that to even show up. So what we're going to do is we're going to neglect the mass of the ISS as too tiny to matter. But that's not something that would be obvious. So do you guys see where I have up here mass of Earth plus mass of ISS? I'm actually going to erase it and just replace it with the mass of Earth. That would not be possible if it was M1 times M2. It's only possible because it's M1 plus M2, all right? Okay, I think we're finally ready to go here. So now that you've gotten through the preamble to the Constitution, you're ready to write the thing itself, all right? So let me erase some stuff here, and I'm gonna kind of set the equation up for you. I'm gonna have to erase the diagram, but could you guys do me a favor? Could you include the diagram as part of your lab submission? Is that something you, thank you. It doesn't have to be too pretty, just draw it out there. Okay, so the first thing that I'm gonna do, I'm gonna kind of square root both sides so I can write down P equals, make sure that you make a nice big neat square root, which will keep everything inside of it. And we're gonna do 4 times pi squared. For reasons that have to do with units, we're gonna put the A in parentheses. You are not gonna have to type the A in parentheses unless maybe you're Adrian, because Adrian's using a line entry calculator. But everyone else will not need to use the parentheses, they're there for the units. So the A, what did you get, Janabella? It was 6.8 million meters, right? I'll put the units in blue. That's cubed. Divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared times the mass of the Earth, 6 times 10 to the 24 kilograms. The first time you punch this into your calculator can be a little bit of an adventure. So we're going to have to strategize. Listen, a lot of the misery that you are going to go through on your test next week is trying to figure out how to plug this stuff in without screwing it up. So we all have to practice together. And Nick, you too, because I don't want you hitting times when you should be hitting multiply or vice versa, okay? So we all need to practice this. Now listen, let me talk about our strategy. I'm going to multiply these through. When I get here, I'm not going to use parentheses. I'm going to hit cube. The most important part is when we get to this point here, we're going to hit divide instead of times. And you have, why, Megan? Okay. Megan, let me explain why. Do you know the answer to this math problem? What is 6 divided by 3 times 2? What's the answer to that?
1.
Now watch what happens. Let's plug it into your calculator, right? Do 6 divided by 3 times 2. That's not 1, is it? Let's take a look at what happened there, because this has to do with order of operations. I told the calculator to do 6 divided by 3. As soon as I hit times, it calculated that quotient and got 2. And then it did times 2 to get 4. That means the calculator thought you wanted the 2 to be up on the top. On the other hand, watch this. If I divide twice, the calculator knows that both 3 and 2 are on the bottom. 6 divided by 3 divided by 2 gives you 1. The moral of the story, Megan, is that whenever something is in the bottom, you want to hit divide. But I had to use this as an example because it's going to be way too confusing with all these numbers. You're going to get real confused, you know? So even though it says times, you got to always hit divide when something's in the bottom. We're going to see this rule many, many times in this class, all right? Okay, so why don't we just try to punch together and let's see if you guys can get it. I'm going to walk you through this one first time around, all right? Let me cut down on the glare here. Okay, clear out 4 times. We're just going to hit EXP to get the pi. Now we're going to square the pi by hitting squared. Now we're going to hit times. You should see this on your calculator. 6.8 EXP6. We're going to cube that. So shift, and there's your cube. Now we're going to do divided by 7 EXP negative 11. And then, Megan, the all-important divided by 6 EXP 24. Now we're going to hit equals. But now we've got to square root the whole thing. So shift, square root. All right, one of the important things about this exercise, the whole reason I made this a lab and not merely a lecture or a homework problem, I want to work with each and every one of you to make sure that you can get this, because this is a sticking point in the class. Everyone hold your calculator up to the screen and show me what you got. Megan, you got it. Nick, you got it. Andrew, you got it. Olivia, you got it. Tim, you got it. Destiny, you got it. Wait, Destiny, hold it up again. Let me just check something there. Is there a power there, Destiny? Destiny, wait, I need to full screen you. Sorry, Destiny, I'm not trying to pick on you, just help you. Can you hold it up to your fan again? Oh, Destiny, it's really weird. You have the right lead digits, but you've got this wacky power. So something went wrong, Destiny. We got to try that again. Who else didn't I check out? Jenabelle, did you show it to me?
Yeah, but I messed up at the square rooting.
Okay, so Destiny and Jenabelle, we're going to try that again. Adrian, what'd you get?
My calculator died.
Now, this is another reason in favor of the Casio FX260 Solar. This calculator, Adrian, which is available for $9 at your local Walmart, will never die. You know when it's going to die? 4.6 billion years from now when the sun runs out of nuclear fuel. Okay, so this calculator is superior to your calculator in every respect.
I forgot to change the batteries out, and I only remembered right before class started, and I went, right.
I'm just teasing you because I can. Well, Adrian, the good news is that you have some math chops, but I was curious to see if you were going to pull this off or not. We have to do this again for Destiny and Jenabelle's sake. So are you guys with me?
Yes.
All right, let's just try that one more time, okay? And if I'm going too fast, you got to let me know, and I'll slow it down. Here we go. All right. So clear out. So I've got some mega glare here. So 4 times pi squared times 6.8 EXP6 Now we got to cube it. Shift, don't cube root it, cube it with that key. Janabelle, do you have this on your screen so far? What about Destiny? Where are you, Destiny? I can't see you. All right, thumbs up. Now divide by 7 exp negative 11. Now divide by 6 exp 24 equals, you should see that number, then shift square root. Show me your moves. What you got?
Is it shift square root or shift? Not. We're not gonna hit the Q3, right? Just the square root.
That's good, Destiny. Yeah. Hold on. Janabelle.
I just pressed shift, so I didn't do anything else after yet.
All right. So this is your square root right there. Destiny, it worked for you this time. Yes. All right. Everyone's got it. Yay. I hope you can see why this was worth making this a lab. That is one of the hardest formulas you will encounter in this class. And there's a lot of places where you can screw it up. In fact, I know the reality is you're probably still going to screw it up going forward, but at least you did it right once and you know how it should go. So let's, Janabelle, what do you think we should round that to? Oh, sorry, I just realized that Ernest is a non-video participant. Ernest, I can't see you, or I have no idea what the hell you're doing, but I hope you're getting that too, because that's very important. So what should we round this to, Janabelle?
You're gonna kill me right now. I cleared it because I wanted to try it again. One last
Okay.
time. So I'm gonna do it again, okay?
That's okay. Megan, what do you think? Oh, hi, Ernest.
Hey, what's up?
Did you do you have your Casio? Did you plug this in?
I don't have a Casio. I got one of these.
Oh, those bad boys. All right, I can tell you how to do it with one of those too. Why don't you start by hitting your square root key? Mine's a little different than that one. I have a big old Casio somewhere. So what you should do, Ernest, find your square root key, and then you got to open parentheses, okay?
Okay.
So do you know where your square root key is?
Yeah.
Okay, good.
Oh, you can't even see it.
It's a little dark, yeah. Oh, by the way, if you ever want to increase your brightness, you hit shift in the up arrow, or sorry, second function in the up arrow. That will increase your brightness so it's not so dark. If I have my, I have my Casio here somewhere. Hold on, buddy. All right, so do you have your square root?
Yeah.
All right, so do 4 times, you should have a pi key right on the front there. Pi, and then there's a square key you can activate. It's a little hard. Wait, which model calculator are you using? Because I'm going to type this into Google. By the way, Ernest.
It's the TI-84.
The TI-84, okay. It's a classic calculator, but consider getting ours too. So TI-84. I just need a big image of this. Because yours, if you're typing it, I can't really see it. Where are we here? All right. So, so you'll do, here's your square root key. So you have to do second function square root, right?
Okay.
Open your parentheses.
All right.
4 times, your pi key is up here above your caret.
Yeah.
So second function pi, you can hit square key next if you want.
Should I put that in parentheses or no?
Nope. Nope, because we're going to do it with proper order of operations. So hit square key.
Right.
Now times, and these instructions are good for Adrian as well, all right? So you just did squared, right?
Yeah.
So times
Okay.
6.8.
6.8.
Now hit second function, and your version of the EXP key is the double E key. So hit double E.
Oh, okay.
6.8 double E 6.
6.
And now just do caret cube.
Caret cubed.
Divide by 7 second function double E negative 11
Double E negative 11.
divide by 6 double E 24. And now you've got to close your parentheses because you're square rooting it from the get-go.
Okay.
And now enter. What do you got?
I don't know if you can.
You've got the right answer.
Okay.
Okay. But I don't want to say the right answer out loud because I want you guys to tell me how to round it. So I was asking Janabelle, did you get it again?
I did not. Nope. I don't know how to. I messed something up. One button.
All right. Well, hold on. I guess we've got a little bit of time, so let's just here. Follow with me one more time, okay? Oops. 4 times pi squared times 6.8 exp6 shift cube divide by 7 exp negative 11 divide by 6 exp 24 equals, and then shift square root.
Oh, that's the last part I didn't do.
Oh, you have to square root it, yeah. It's so easy to forget one of these steps. So Janabelle, what do you think we should round this to?
Just 5,436.
Round it even more.
Okay. 5,444. 444.
Wait, it's 5,000.
436.
Forget the 36.
Okay. 4,400.
5,400 is what I want.
5,400. Yeah.
So 5,400. What are your units?
Meters.
No, P is a time.
Okay.
Can I ask why you rounded out the 36?
Because it's fucking bullshit and it's not real. I don't know how else to say that. All right. Okay. All right. So wait, Megan. All right. Now that I've got your attention, how many significant figures does this number have?
2.
How many does this have? And that has 1 as well. Megan, I probably, even keeping the 4 is a little bit suspect, but the square root softens the fact that I rounded these numbers really hard. Plus, I over-rounded this and I under-rounded that, so they kind of works out a little bit. But Megan, even the 400 is suspect here. Do you understand? The 36 has no bearing on reality whatsoever. Basically, 2 sig figs in means 2 sig figs out. The 36 is just, it's not real. But I want to know the units. Do you know what the units are, Megan?
Years?
That was in the Kepler version. We're doing Newton's version. This is an MKS formula.
Second?
Yeah. Meters cubed cancels with meters cubed. Seconds cancels, kilograms cancels with kilograms. 1 divided by seconds squared is seconds squared. And the square root kills the square. 5,400 seconds. Now, box that. While that is our answer, it is customary to convert your answer into some sort of unit that is in good taste. For instance, Megan, if I were to tell you that this class was going to go on for another 5,400 seconds, would you know what that meant? How long would you be here?
$90 minutes.
Oh, good. Okay, so 5,400 seconds if we convert that from seconds to minute, 1 minute is 60 seconds, right? And that gives us about 90 minutes. I'm just kidding. I'm not going to make this class go on for another 90 minutes. That would be cruel. All right, but that's how often it takes the ISS to travel overhead. Now, before we end our lab, and I want you to know we're getting out even earlier than usual, which is kind of nice. I want to share this really cool YouTube with you guys that you might want to watch sometime, especially if any of you have a high resolution plasma screen that's 4K and you can go onto YouTube through your PlayStation or whatever you guys do. There's a YouTube video called Orbit, a journey in real time around Earth. And basically they just took a video from the cupola of the ISS and made this super dope 4K video of one orbit of Earth. And they put cool techno space. I'm gonna put that in quotes. Yeah, exactly. Some rave, you get your rave on, okay? And it's just so incredibly beautiful when you have a high resolution screen. Sometimes I'll just like make a sandwich and I'll just put this on in the background as like my lamp or something, you know, just watching the Earth spin underneath you. And it's really beautiful, especially the nighttime parts, to see all the cities of the Middle East stretched out across, like, I think that's the Red Sea right there, I'm pretty sure. So, where's my goddamn geography? They're going over, Ethiopia and Sudan. I forget what that city is there, but I don't know if that's Djibouti or whatever. All right, my Middle East capitals aren't so good, guys. I'm sorry. Anyways, it's just cool to look at all of this human civilization stretched across the desert and to realize that we're kind of like, you know, when I look at this, it kind of makes me think that we're kind of like the Borg in Star Trek or something. We're like this technological, electricity-loving tick that lives on the surface of our planet. And we've got our networks spread out like a big electronic hive all across the surface of the Earth. It's really beautiful. The daytime stuff is pretty cool too. There's a couple of different versions of this, but this one's particularly noteworthy just for its really high resolution and beautiful views. So I'll put that in the chat log in case you guys want to peep that at some point. It's kind of cool. And there's some other really neat versions too, where you can see things like fires and other things going on. Like, I think they did a couple of cool photographs of one of the latest hurricanes that was in Florida, and it looked absolutely insane just watching the hurricane travel across the globe. All right, so before we end our lab here, let's have a chat about some things. First thing, I'm a little behind on the grading. You may have noticed. I'm going to get to that. On my Tuesday and Thursday class, they basically, they tend to just, they were watching my videos with no participation whatsoever, so they get the pre-recorded lecture because that seems to work for them better. So that'll free up some time for me tomorrow to catch up on grading. Both their class and your class, I'm going to put the test back until next week. So you guys will take your exam on Monday. That'll give me some time to finish up putting all the multiple choice questions in place. Next class, we will have a normal office hours, a lecture, and a lab, okay? So next time I see you guys will be 10 a.m. on Wednesday, correct? Okay. We can't have the day off of homework every day. Just today it made sense. So we'll do homework, lecture, lab on Wednesday. At the end of lecture, I'll give you guys a heads up of what to expect on the test. But I want to let you know in advance that we're probably going to do an office hours the day of the exam. But instead of doing a homework that day, we'll do practice problems for the test. That'll be kind of like a little dry run of what questions to expect.
I'm sorry, so there was no homework today because I joined Zoom a little late.
Yeah, I don't know if you saw my email, Megan, but I knew that the last lecture ended at Kepler. And the next homework we have to do is the chapter 4 homework, which you've just learned the material on. So the homework would have just been way too crazy to do. And while I could have given you a different homework, I decided to just give you the time off instead. I figured you'd like that. Okay. So, so yeah. So, oh, Janabel?
Go ahead. I thought you was done. Sorry. Go ahead.
I'm sorry. Can you say that one more time?
I thought you was done. I interrupted you. I'm sorry.
Oh, no. I don't even remember what I was going to say. So.
Okay. Sorry.
That's
How does
okay.
testing work during distance learning? Like, is it just a test you post on Blackboard?
Yeah. So last summer session, it was my first session giving the test. And I was so kind of behind that I ended up just giving the students a Microsoft Word document, and they highlighted the answers and emailed it back to me, and it was a total piece of shit show. So there is a function for me to give you an exam through Blackboard where you kind of log in and it will deliver the questions and you click the right answer. That will be both better for you and for me. But the problem is, Janabel, it takes a wicked, wicked long time to make it. So I have a head start. I'm currently at question 60, and I got to make sure I can finish it before Monday. So I'm going to try my best, okay? If things go badly, I might give you the Word document. But in any case, let me explain this, Janabel. I've always been a little different about my tests. Some professors just kind of say nothing, but I like to treat the test as a full contact sport. I like to be around and be available so that if you guys get in a sticky jam, you can ask me for a hint or a little push, or I can help you explain a question better. Basically, I want to be around to help, okay? So what we'll do is, even though we're all taking the test in isolation, I think we should have a day where we all kind of like log in just like this with all of our windows shared, or, although you could mute it, I guess, if you want. Not so that I can monitor you, but more so that like I can be doing work around my apartment, or who knows, maybe I'll vacuum the dust bunnies under my couch or something. And then I'll have the audio on the computer on. And if you get in a jam on question 56, you can say, hey, Brendan, I got a question. And I'll come over to the desk and I'll say, okay, what are you working on? And I'll share the audio with everyone because your hint might be a helpful hint for everyone. You know what I mean?
Yeah, that sounds good.
That sounds pretty good. That way you're not like just thrashing around in the dark. I've often found too that sometimes you can get to a set of questions and you can be like deer in headlights, just stumped. But if I give you a little hint or a little push, that's enough to get you going through it. So I'm not opposed to giving you a passive aggressive hint from time to time. So we'll probably log in, but you'll probably be, everyone will kind of mute themselves, including me, and you'll be clicking the multiple choice buttons. That's what I hope it's going to happen like, okay? All right. All right, so guys, and especially you, Ernest, make sure you're submitting all of your work, okay? I noticed that I saw a lot of work getting submitted, and I'm very proud of you guys for keeping up with it. Now, when I grade tomorrow, I'll find out who's been naughty and who's been nice. So please get all that work in so that you guys can all get a good Christmas gift, all right? Any other questions before I end class today? All right. Well, great hanging out with you as always. Live long and prosper. Thanks for telling me about the comet. And I will see you guys on Wednesday at 10 a.m., okay? 10 a.m. on Wednesday.